Okay, perfect. Then, hello everyone. I hope you can hear me fine. I see you as a tiny window on the edge of my screen. So if you have any question, feel free to also I much prefer interactive sessions than just giving a sort of lecture. And as Carlos mentioned, I did AstroCamp so 9 years ago already. And at the time, I was very interested into astrophysics, and I'm still very interested in it. And I did in my academic career a bit of a full circle, and now I'm back to actually using technology that is in space, but this time in order to observe the Earth. And this is what we call remote sensing for Earth observation. And I, through my master's, so I did a master's in geophysics, and I did a master thesis looking at using remote sensing for glaciers. And then I'm currently doing a PhD in Switzerland at ETH Zurich for agriculture. And so I took on the task of presenting a bit how we can use remote sensing for Earth applications, and specifically with those two case studies, because this is what I've personally been looking at. So what is actually remote sensing for Earth observation? During AstroCamp, you hear a lot about remote sensing, but for even more remote objects like stars. But this time we're really looking at, let me just use a laser pointer. Using a measurement device. It could be a satellite, it could also be a plane or a drone. And then you acquire images of Earth, either using passive remote sensing. So this means that you only use the sun as your initial signal, or active remote sensing, where your tool of measurement also um, like delivers a signal itself that you receive afterwards. What's interesting with these tools is that they are super scalable over space. So you don't have to go in the field like in person and take a lot of measurements by hand. Whilst this is good for calibration and validation, if you want to be able to observe Earth on a much larger scale, satellites, for example, are a great way to do so. Something that you're probably familiar with right now is that according to what you look at in the electromagnetic spectrum, you can observe different things. So these are a bunch of satellites that exist and have existed. It's not all of them, obviously, but only a selected few. And according of where they are on the electromagnetic spectrum, they observe different things. So the Fermi satellite, I believe, is from NASA. I'm not sure. This one uses gamma rays, and here it mapped out the Milky Way using a gamma ray map. Hubble, here the telescope is between visible, a bit of infrared, a bit of ultraviolet, and you have beautiful images of galaxies. Planck has been used, and this one is in the microwave domain, and it's been used to map the cosmic microwave background. And the satellites I'll be talking about more specifically that I've been using are in the microwave domain, and they're called Sentinel-1. And they were launched, and they are the propriety of the European Space Agency. So anything that goes on in my presentation for a lot of the results that you'll see are from the Sentinel-1 satellites, but there's a lot more that can happen also outside of this if you use different satellites. But why would you actually want to use different satellites where actually then you would have different physical properties? So if you look at the optical domain, so for example, a satellite called Sentinel-2, which is also by the European Space Agency, this is Porto. On a day where maybe it was a bit cloudy, then if you use an optical imagery satellite, you will not see below the clouds. It's just like us humans, how we see with our eyes. If there's a cloud, anything that is behind, we will not see it. But if you use the microwave imagery, such as with Sentinel-1, this time it penetrates through the clouds, so you actually can see through them, which I think is super cool. And this time you need to make sure that what you interpret here, the image of Porto, is not the same red, green, blue channels that you would have in the visible sense. But here you're looking at polarization, and I'll go a bit in more depth into that. But here I just wanted to show you that if we take a case of Porto that we know, and we observe it from space with satellites, according to what they acquire, we would see different things. Another thing that we need to take into account is that spatial resolution is also important to consider according to your problem. So here again, we look at Porto. This is just a Google Maps image. If we put another satellite, which is called MODIS, and this one is 1 kilometer resolution, you're not going to see much. It's going to be super pixelated. So you would not want to use MODIS for a specific city, for example. But if you zoom out, then you're able to see the physical parameters distribution over a large, wider range on Earth. And this is a lot more interesting, for example, for global comparisons. So another consideration for remote sensing is to question what do you want to look at. And according to this, it would guide you towards choosing the correct tool. And in this case, maybe it's for global temperatures, then you would want to use a MODIS satellite, for example. But as I mentioned, I've been focusing on Sentinel-1 satellites. And one question is why? Sentinel satellites from the European Space Agency are very easily accessible. The data is free. And there's quite a high coverage on Earth. And they have a spatial resolution of 10 meters when you're inland. And it's a bit more when you're out of land if you're looking at the sea. But basically, they're one of the highest resolution satellites that you can get for free for Earth observation practices. So in microwave imagery, I mentioned that we can look at polarization of the wave, and I'm not sure, I don't remember from AstroCamp if this is something we deal with, but here is a brief overview. As the electromagnetic wave propagates through a medium, it can have different polarizations. So, for example, if it propagates in the vertical axis and you receive it in the vertical axis, this is called the VV polarization. Opposite, if it's in the horizontal axis, it is possible for you to send a signal in the vertical axis and then receive it in the horizontal, and the inverse is also true. So usually when you acquire a signal for Earth application purposes, you will acquire a certain state of polarization. And this is quite interesting to do some further analysis. So you can assess over time. So if your satellites goes through and acquires an image over a same target at different times, then you will receive different polarizations. And this tells you about how the signal is interacting with your target. And by this, I mean, how does your signal scatter? And according to how it scatters, then you're able to interpret properties about your target. So here is a very brief example about crops. Over time, you can see that the magnitudes and the phase change, and this can tell you about the state of the crop. You can also look at entropy and alpha, but this I'll go a bit more in depth. Another thing you can do is called interferometric information. And why this is interesting is that you can get super high precision differences between the phases of different acquisition. And this tells you about land deformation. And it's specifically used for landslides, earthquakes. There's a typo here. If volcanoes are about to burst, then this you can also monitor with interferometry. And these are really the two main pillars of using microwave imagery for Earth observations. So case number one, monitoring of crops. This is what I'm currently doing as part of my PhD at ETH. And I just wanted to explain the rough lines of what is possible. So there was a field campaign in the last months, so from April to July, where we measured soil moisture from the ground. And this took a lot of time because it's probably like many hundreds of measurements every given day of field campaign. And it's multiple of those days across many months. So it requires a lot of time, a lot of resources and energy. And we wanted to compare how the signal from our satellite behaves when we look at a here is a corn maze, here is a potato maze, sorry, here's a cornfield, here's a potato field, and this one is the wheat field. And this is close to Germany. It's in Germany, but close to the city of Munich, where those fields are right now. And then over time, from the time that we plant the seeds of the plant of the crops, we can see them develop, and we can quantify what is called the phenology, which is at which stage of growth is your crop in. And there's different stages. There's a whole bunch of theory out there, but you start with germination, then your plant starts sprouting, and then it forms leaves, and then you have stem elongation, then it flowers, and then the fruit ripes, and senescence is basically when it's ready to be harvested. And you can track those stages for each crop. So here we started on the 16th of April and we finished on the 23rd of July. So it's quite satisfying to see the crops grow, literally speaking. And so why do we actually care about this? Well, you have your ground measurements, which is soil moisture. For example, here, I compared with some optical satellites, Sentinel-2, for a vegetation index. So how green is the plant over time? And you can see that the x-axis here is the date from the start of the campaign to the finish. And then I can also correlate this with my microwave satellites metrics. So you have your VV polarization, you have your VH polarization, and then you can calculate entropy and alpha angles. Now, what does entropy and alpha angles actually mean? It's concepts in physics. So entropy, you probably know about it from physics. Alpha angles is quite specific to remote sensing and to scattering theory, but entropy is the measure of randomness. You measure it from 0 to 1. Low entropy, there's one dominating scattering mechanism. This could be a building, for example, has very low entropy. High entropy is there's many random scattering, and this could be a bush or like huge vegetation, because of all the leaves are interacting with the signal and they're considered random scatterers. Alpha angle is another metric, on the other hand, which tells you not about the type of randomness, but the type of scattering mechanism, where you can have a surface scatterer, and this is if your alpha angle is 0 degrees. You can have a volume scattering, like vegetation, if your angle is 45 degrees. And then you can have a vertical object, which creates this angle here. And this is called double bounce because it bounces. So your signal comes here and hits the ground. It bounces off to the vertical edge and then bounces back towards your satellite. And so if you track where your alpha angles are, then it tells you what type of scatterer you're looking at. In scattering theory, if you compare the position of your measurement according to alpha angle and entropy, so alpha angle is on the y-axis here, entropy on the x-axis, then it tells you even more in details the type of structure you're looking at, according to how random it is and what type of scattering you're at. So this is a result from a paper that has been published, which compares different types of land. For example, the pink triangle here is urban area, so you expect it to have very low or at least lower entropy, because the buildings are not so random by nature, compared to land which could correspond to agriculture, for example, or some type of grasslands. Yeah, and so basically you're able to assess using polarimetry, so alpha angles and entropy, on which type of target you're looking at. And so if I do those calculations with my crops, this is an example for corn, maize. If I plot the alpha angles and the entropy over the growth stages, oh, here I forgot the legend, but the darker green corresponds to germination, when the plant has not even come out any type of vegetation. And then the more you go into the orange, the more the plant has grown. So here you can see over time that using alpha angles and entropy, you are able to assess using satellite imagery in what specific phenology stage your crop is at. And in the bottom plot, I calculated what I call the mean trajectory, and by this, you just calculate the mean position per stage. So, for example, your germination stage 0, the darker green, would be lower entropy, a lower alpha angle, and you can see that as the stage progresses in the growth of the crop, the more you can actually differentiate where they're standing in this in these metrics. And so using polarimetry, you can actually get more information about the growing stage of your crop. And this is interesting for yield prediction and just general monitoring. And I think it's pretty cool that on such a small scale of just one field, you're able to already identify using a satellite, which is hundreds of kilometers away from you, in which stage your crop is at. Another case study that I wanted to mention is the glaciers, and this is work that I've done as part of my master thesis. Glaciers are, I don't know how familiar you are also with them, but they're right now, with the climate crisis, melting extremely fast. And whilst it's important to also go in person and assess the nature of the damage, satellites are able to monitor them, specifically the ones that are in isolated and extreme environments where you could not put humans in there. The glaciers I specifically studied are belonging to Norway in Svalbard, so they're above the Arctic Circle. When I did my master thesis, I lived for a few months also above the Arctic Circle in Tromsø in Norway. And this is Svalbard here, so as shown in the circle. And these are the two glacier complex I looked at. Holte which is in green, and Kongsvigen, which is in purple. And this was a partnership with the Norwegian Polar Institute because they themselves use people to go in person to Svalbard to monitor the glaciers, and they wanted to corroborate their field measurements with satellite imagery. So this is a bit of a drawing on the anatomy of a glacier, because before I even started my master thesis, I personally didn't hear much about them, and it took me a while to actually understand that there's different types of snow and different types of ice. The more you go to the left on this plot, the higher you go in altitude, and the higher you go in altitude, the more you have dry snow. And the lower you go in altitude, because of the temperatures, the more you have wet snow. Basically, over time, as you're in positions in the mountains or Arctic or Antarctica, which are very cold, sometimes you have snow events and snow accumulates. And as it accumulates, that means that the bottom layers get more and more compact. Your microwave signal is sensitive to the dielectric constant, which means that any change in terms of wetness of your medium is able to detect. So this is actually quite interesting, that there are different types of snow and different types of ice, and this could be perceived by your satellite. So I mentioned here in the high altitudes, you have just dry snow, which compacts. In the lower, you have more wet snow, but also glacier ice. And in the middle, you have what is called superimposed ice, which is ice that has been going through cycles of freezing, melting, freezing, melting. And then it has those ice layers in between. And these can also be identified with satellite imagery. According to where the zone is, you have those lines. So the dry snow line, the wet snow line, firn snow line, equilibrium line, which tell you about where the different zone delineation is. And if you map those over time, then you're able to monitor your glacier's behavior. So this is what it looked like for my glaciers. So if I focus on Holtedalsfjordna here, which is the bottom glacier, on the left is just the Google Maps image. In the center is what you see with the microwave imagery, so the Sentinel-1 satellite. And on the right is a picture that was taken on the field. So this orange box here, and also the one that is here, corresponds to Fern. Fern is as dry and compact snow as you could get. And it is shown in microwave imagery as very bright and intense compared to the other layer. Okay. So for superimposed ice, as you can see on the right image, it's quite wet because of this cycle of refreezing and remelting. Um, and when it shows in the satellite imagery is between the firn, high intensity, high brightness, and the glacier ice, which is a lot darker. Um, for glacier ice, on the glacier I focused on here, so Kongsvigen, you have two different textures according to where you are in your glacier. So the blue box is the one that is the most upward in altitude, and this is quite hilly. And then the green box is the one that is the closest to the sea, um, as shown here. And this has some quite rough patterns. And these are old drainage channels of the glacier that you can actually spot. So the upper photo was taken on the ground. You can see the footprints. And this green picture was taken from an airplane. So it shows you also quite the scale of the glacier. And then we have this red box here, which is on Holtedalfuna. And this is just crevasses. And you can see them in the microwave imagery as being super bright, which looks a bit like fern. But maybe you can spot them also yourself. There are patterns, which are quite random for sure, but they're still, like, let's say, breaks in the ice because the crevasses are due to this compression of the glacier ice. So, technically speaking, a crevasse type is glacier ice, but it looks very different from both microwave satellite imagery and when you go see it yourself. So, a bit about the geometry of satellites, because this is actually super important when you interpret the acquisitions. Um, your satellite here is the radar antenna, because we're looking at the microwave imagery. So, your satellite sends a signal. It's an active remote sensing measurement, if you remember the first slide. And what you have is this thing called an incidence angle between your signal and the norm of your target. And your incidence angle can be in near range, which would be here, or it could be in far range. And your radar has this footprint, which means it captures the image over across quite a wide and a long scene. So it doesn't just capture one pixel, but it captures multiple. And why this is actually a problem is that the signal you will get from near range, because of the incidence angle being very short, you will actually get a higher intensity. And the signal you get, which is further range, you will get a lower intensity. And this is called the intensity decay because of the incidence angle. So this is purely a geometrical problem that you have to take into account when you look at your satellite imagery. Now, during my master thesis, what I looked at is this specific problem and the fact that if you have different classes, if you look at different zones of your land, and for me it was my glacier, they behave in different ways. So the intensity decay has a slope which is affected by the dominant scattering and also the surface roughness. What that means is that if you have one type of ice and another type of ice, they can have an intensity decay which is different because the slope um, is a function of what type of medium you're looking at. And usual corrections would do some type of averaging where in the pre-processing, before you even analyze your image, you are trying to make your image as clear and interpretable as possible, but that means that a lot of the time you make a lot of approximations. And one of the approximation that is standard in remote sensing is that you just take the average of all your classes, and this means that you lose a lot of information. The problem with this is that means that you over or undercorrect certain classes of what you're looking at specifically. And this is problematic when you try to classify. For example, what I tried to do here is classify the glacier zones. What is firn, what is superimposed ice, what is glacier ice? And if in your pre-processing step you approximate and over or undercorrect classes, that means you lose a lot of information, and that means your classification outcome will not be as accurate as possible. I won't go into the details on the actual classification algorithm, but what I did was to calculate the intercept and the slope, because here we assume that it's linear for each class, and then feed this into my classification algorithm, which was a Bayesian classifier. What this gives, so I wanted to show you first what happens if you don't have any correction. So the orange here is the firn. Okay, I see I have 10 minutes left. The purple is superimposed ice, and glacier ice is blue and green. So this is without any type of correction. This is the standard way of doing the correction, and you can see that you can already observe the different classes a lot clearer. And the red circle here are the crevasses. And this is implementing the correction that I developed in my master thesis, where you can see that there are quite some differences in how the classification is done, or like what the output is. And the crevasse area is still very much misclassified. What you can do with this classification is that if you do it over time, you can map out the lines that I mentioned before that exist on a glacier. And here, this is the snow lines, and I mapped it from 2017 to 2023. And you can measure the distances of the differences. Here for Holte-Dalfona, you can observe that between 2017 and 2023, there was a large extent that was considered firn that has been broken down because the glacier just melted. So there's around 3 kilometers stretch of glacier that is not anymore firn because of the melting. And for Kongsviken in the south, there is on average a couple hundred meters of retreat of the glacier. And this would mean that the glacier has melted between the summers of 2017 and 2023, and this actually maps with all the heat records that unfortunately we keep getting every year. But yeah, this is from 2020 and this is from 2022. So with this new method of pre-processing, we can map and classify more accurately glacier zones using satellite imagery, which is extremely scalable, and probably costs a fraction of the amount of resources that would be required to do this on the field for many different types of glaciers. So in general, this was quite a high-level presentation. This is a photo of crops with different scattering mechanisms, which I think looks quite cool. And I wanted to show you in this presentation that remote sensing for Earth observation involves that you can measure and monitor Earth in a very scalable way, but you need to adequately think of what problem you're actually trying to solve. This means what type of spatial resolution you want, what types of physical properties you want to measure, and also how do you actually pre-process your data, because this will impact on what you're actually looking at. And with microwave imagery, which is my specialty and the satellites I'm using right now, there's many different types of analysis you could do. Polarimetry analysis, looking at those VV, VH, HH, HV. And I've shown you an example for crop growth. There's also backscatter intensity analysis, which I've shown you for glacier zones, and interferometry analysis, which I did not go in depth, but where you can also measure deformations of land, such as earthquakes and landslides. So this is it for my presentation. Thank you so much. I think we have around 6 minutes and 30 seconds for questions before the Zoom call ends. So yeah, you can always reach me by email also if you have any questions or if you have any interest in either the organizations I was involved in or the topics. I'm always super happy to share and to answer any questions. Thank you very much.